Hi, this is the Related Rates video. I bet you're excited. I know I'm excited. Are you excited, Ms. Schwartz?
I'm excited, Mrs. Lemke. I'm glad that you're excited.
Okay, so as you can see, we have a sentence here explaining what related rates are. Related rates are basically rates that are related, I know, but when two or more things are related by some kind of an equation or relationship, then if you take the derivative of both sides, then you get rates that also will be related. And so when we take the derivative, what will our independent variable be in these questions?
Ooh, that's really hard. I mean, if we're thinking about all these things changing as rates.
Oh, like that would be like per hour or per minute?
Maybe per second.
Oh, so time.
Time.
I get it. But before we get into all that today, we want to make sure that you know your older stuff, like just the skills for related rates. And so here's a warm-up problem. We'd like you to pause the video and then come back and find out if you match us. No cheating. Don't look ahead.
Make sure you're taking the derivative with respect to time. All right, so hopefully you paused and you actually tried on your own. You didn't just listen for 3 blank seconds and then wrote down what we wrote down.
No one would do that.
No.
That's cheating.
All right, so if you look here, I've got things color-coded. We have our red function and our green function, and the operation happening between these two is?
Multiplication? Oh, that makes it a product.
Product rule.
Yay!
First times derivative of the second plus the second times derivative of the first. Then we have our blue function, purple function, and the derivative of a constant?
0?
Always.
Nice.
So looking at this derivative, we can then substitute in all of our known values. And just like magic, the last thing that's left to find is our dx dt.
Oh, okay. So why didn't we do anything else with that function, with that fraction? Because I think I could do something else with it, couldn't I?
What might you do?
Couldn't I simplify it?
Would you really want to risk simplifying and making a mathematical error?
Oh, yeah, then I would lose an answer point potentially. So, yeah, I guess that's strategically smart. But I have another question.
Yeah.
Why is the rate negative? Isn't that, I remember there being a thing you said the other day about, like, the rates being positive and negative and that mattering somehow?
Yeah, can you remember why that matters?
I can't, that's why I'm asking you.
All right, so if we think about negative rates, that means our function is going...
Oh, downhill. So shrinking. So that means that x is something that's getting smaller over time.
Over time.
I see.
But that means that if our rate was positive, x would be...
Growing?
Exactly.
Cool.
All right, so now let's talk about how these rates are related to each other. What we have here are guidelines. Please note, guidelines, not a step-by-step process
So it's
for
not-
everything.
I see. So it's not like a recipe. It's more like if I get stuck, I could just look at that list and see what I forgot to do.
Exactly. But, Mrs. Lemke, I think there's 2 important things here that we want to clarify.
Oh yeah, there's something that has to happen before something else. I know students of mine in the past have gotten confused about this. You have to make sure to take the derivative before you substitute in values. If you think about that, if you plug in the values first, then a whole bunch of things are going to go to 0 because like we said with that last warm-up question, the derivative of a constant is 0. So if everything was substituted in, we get a bunch of zeros in the problem. That's not going to be a thing. So we always have to differentiate before we substitute.
And just a reminder, what does it mean to differentiate?
Oh, take the derivative.
Oh, okay.
Okay.
All right, so thinking about how we can create rates that are related, before we can relate them, we need to understand that they are rates.
Okay.
All
So
right.
we need to actually figure out like what's going on in the story.
Yes.
I like how the story has a name. Do all the related rates problems have names?
Most of them do, and if not, I encourage you to make up your own name for the problem.
I like it. I'm going to go tell Mr. Code today that I did the Pebble problem.
All right, so let's talk about the pebble problem.
Okay.
You guys know how to read, but I'm going to highlight important information. So
Well,
we've got...
I can read and you highlight. How about that?
Okay.
Okay. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So that means they have the same center. So it's like bloop into the pond and then rings of water. The radius of the outer ripple, so like the biggest circle, is increasing at a constant rate of 1.2 feet per second. When the radius is 4 feet, so that doesn't happen all the time, but there is a moment in time when the radius will be 4 feet. At what rate is the total area of the disturbed water changing? Disturbed water? Oh, they mean the part with the ripples.
that's a lot of words.
That is a lot of words.
Let's maybe translate those to some
Okay,
math.
let's try. Okay, so if we go through there, one thing I remember seeing is the word rate, and it said a constant rate of 1.2 feet per second, and also the word increasing was there, and you just told me increasing things have a positive rate of change. So I think 1.2 is a thing, but I don't know what it is.
So we've got this positive 1.2 feet per second, talking about the radius of the outer ripple. Well, if we think about how the radius is changing
Over time.
over time,
Oh, okay. So that would be dr dt.
the rate at which the radius is changing
I like it.
over time.
But sometime later on, the radius is going to be 4. Most of the time, the radius is a variable, like r is varying, but there's going to be a point sometime when the radius is 4. So I like that we labeled that later. What is it we're trying to solve for?
I think it has something to do with the total area, but I'm not really sure how area and a radius would relate to each other.
Oh, well, they're circles, aren't they?
Yeah.
So I think we want to write the area formula for a circle.
I remember from my PSGA class that the area of a circle is pi r squared.
I like it. So what we're actually trying to find, if you look at the last sentence, it said, at what rate is the total area changing? So we want to find the
ADT.
right, the ADT.
But I don't want that all the time. I want that specifically later when...
Okay, so I think first though we need an equation where we have dAdt and we have drdt. How are we going to get that?
I think if I'm talking about rates that relate, I should probably take the derivative with respect to time of this equation right here.
I see. Okay, so it's just like what we were doing in yesterday's lesson, like differentiate but with respect to time. So like area is a function of time, radius is a function of time, because other things will change as time progresses. Oh, look, you've got it. Well done.
Why doesn't the pi go away? Why is
Oh,
the
because
pi
it's a
still
number.
there? Oh, so it's the constant multiple rule.
Right, because it just looks like a variable because it looks so weird, but you have to remember it's really
It's
a
really
number.
just 3.14.
Yeah.
Okay, so now that I have all of my different pieces, I have taken the derivative, which means now it might be time for...
Substituting in, right, because we said like the one thing on that list was you have to take the derivative before you substitute in.
All right, so let's start substituting. Well, dAdt is what I'm looking for,
Yep.
so I want that to stay.
So that better be the only thing that has letters.
I hope so.
Sweet.
So I've got pi.
Okay.
I've got 2.
Yep.
What's my radius going to be?
Oh, it's later. Now it's later. So 4.
And how fast is my radius changing?
1.2, I believe.
All right, let's clean up that answer. And we get approximately 30.159,
Ooh.
3 decimal places.
That's right. At least 3. You could get more. I mean, you can be an overachiever.
But now let's think about what units should go on here.
Oh, it's the rate of change of area. So area is measured in some kind of square units.
So I think we're going to say feet squared
Yeah.
And
then
our time?
Oh, seconds. I see it.
per second.
It's in the story.
All
I
right.
like it. I like these stories that have titles. Let's do another one.
All right, here we have the ladder.
Oh, good. A 25-foot ladder is leaning against a wall. So it has to be leaning. It must be like the hypotenuse, because if it were straight up and down, like the edge of a triangle, it would fall over.
It would fall over.
Okay.
You are correct.
So a 25-foot ladder is leaning against a wall. And this is a very bad ladder because it's sliding down the wall. Maybe the wall's
Doesn't
slippery.
seem safe.
Oh, it doesn't. It's sliding down the wall at a rate of 0.4 feet per second. So
Sliding down.
So it's getting smaller. So negative.
0.4.
I get it. Okay, so that's a rate of some kind. We'll come back to that. How fast is the base of the ladder sliding away from the wall at the moment when the base is 7 feet from
Ooh,
the
a
wall?
moment. That's
Oh,
later.
Later, that'll be after we take the derivative.
And the base is equal to
Okay,
7.
I feel like we should label some sides or something. Could we call the bottom part B for base?
Sounds good to me.
And could we call the up and down part H for height?
I think that makes sense.
I think it helps to use letters that help you understand what they stand for. Like if we just use X and Y, that wouldn't be quite as good. Yeah. Okay. So the negative 0.4. Oh, you were just, that's what I was just going to say. Good job,
I'm way
Ms.
ahead of
Schwartz.
you.
Always. All right. So we need to figure out a relationship between the variables and the problem. Like something that's not calculus, but just a fact that we know.
I think I heard you reference the word hypotenuse.
Oh, so like Pythagorean theorem. I
Pythags.
love. Woohoo!
So in this case, we're going to have our b squared plus h squared would equal our hypotenuse squared, but is our 25 feet ever changing?
It's not, so when we take the derivative, it's going to be 0, but right now it's just going to be 25 squared.
25 squared. So why is it okay to substitute that one in?
Oh, because it's always true. The other things in the equation were variables. They vary.
They vary.
Yeah,
They
I
change.
get it. I get it.
All right, so from here then I have my equation that is relating my variables, but these aren't just related problems, these are related
Rates. We need rates.
rates.
Derivative time.
Derivative time. So taking the derivative with respect to time, we get 2b dv dt plus 2h dh dt. The derivative of a constant is always
0. And that's a place
0.
where sometimes people get carried away and they forget.
Don't want to forget that.
I mean,
Bless
woo! That was a little. I get so excited. Anyway, sometimes people just like forget. And sometimes use some kind of power rule or just bring the number along. That's not
definitely
a
going to
thing.
be 0.
Okay, so we're going to
So
substitute
let's
in now.
substitute. It's later.
So at later, the bottom is 7.
Times 7. We've got our dB dt is what we're looking for. Bless you. So that's going to stay as a variable. That should be our only variable.
Oh, so that means we need to figure out the h that's coming out.
Yeah, because this is
Oh, I know.
Ooh, what do you know?
It's a triple.
It is a triple.
So if the bottom is 7, the hypotenuse is 25. It's 7, 24.
And our dH dt we said was a negative 0.4
No, it's negative because it was shrinking.
because it was shrinking. Yeah,
Got it.
sliding down the wall.
Okay.
All right, so the last thing to solve for is dB dt.
So when you crank all that out, I need to remember the 3 decimal place rule. Right? So
dB dt is approximately 1.371. We're measuring the rate of the base changing, and that was measured in
feet.
feet.
And time was seconds. Fast, sliding down fast kind of ladder
fast.
situation. That's dangerous.
Don't climb on
Okay.
it.
Yeah, wear a helmet. Okay, the next one has a title too.
The
Balloon problem. Oh, I love this one. Let me read it. It says air is being pumped into a spherical balloon. So that means shaped like a baseball. Suppose the volume of the balloon is increasing at a rate of 400 cubic centimeters per second when the radius, that's going to be later.
Later.
When the radius is 30 centimeters. That's going to be later. Okay. How fast is the radius increasing at that time? So what we're solving for is dr dt.
RDT, the
Okay.
radius changing.
Yep.
What do we already know?
Well, we know that it mentions volume.
So our dV dt is going to be 400,
Uh-huh.
and it was increasing.
Oh, so it's like a
Positive
balloon that's
400.
getting bigger. I see.
Yeah.
Okay.
All right, so great, I've got these rates, but I need to somehow...
Well, I think I understand. So it mentions volume, it mentions radius. So, and we know it's a spherical shape. So I remember from a long time ago, volume is 4/3 pi r cubed.
All right, so now
Okay.
we've got our variables related, but again, it's not related problems. It's
Oh, well, it's calculus time. We want related rates. So derivative.
dV dt. Bring down that 3 with the power rule. I'm going to write it separately. We're going to clean it up in just a minute. But the 4/3 pi is just a constant. Power rule would say 3r squared, but we're taking the derivative with respect to time. So now I've got all this, and I'm going to clean it up after I do my substitution.
Oh, okay.
So now it's later.
It is later, so that's when the r is going to be 30. And I think we know, we knew dV dt was 400.
And we've
And
got,
that not only leaves one thing that we don't know, which is a good situation.
and conveniently, the RDT is not only the thing we don't know, it's also the thing
We want to know.
wanted.
Solid.
Clean it all up, and we end up with the RDT is 0.035 centimeters per second. Or, if you want to keep that pi in pi form, it would be 1/9 pi centimeters per second. But why is it centimeters?
Because it's the rate of change in radius. And so what would the radius have been measured in if the volume was being measured the way that it was? Oh,
Linear.
actually, it said it right up here.
Linear measurement.
Ah, it did.
Centimeters.
It did. Okay, well, this has been really fun. I can't wait to come to class tomorrow. I see it looking ahead. There's a lighthouse problem.
lighthouse problem.
It has a title. I
Oh my
love this.
gosh.
This is the best.
Another story.
See you in class.
Bye.